No worries.
This talk's unique. All of the talks will be in a different one.
Okay. No worries.
Okay, so I think we'll get started. I'm not sure the microphone is working.
It's not.
It's not. So I'm just going to project because what I'm going to say is very brief.
She had your dark suit and greasy wash water all year.
Okay, so maybe I need to project into the microphone. So I'm very excited to present as our first speaker of the series, the plenary series, associated to JSALT, John Hansen. He's one of the people we invited from the Diarization team. And for us, it's very important that he's here because he's among the pioneers who have started early work on real-world recordings gathered as someone goes about their day wearing a recording device. And so in particular, he developed the Prof-Life-Log database, which he recorded himself. So he's an actor in it. And also developed the annotations to go with it and did a variety of tasks on it, ranging from event detection to, of course, just speech diarization. And so it's good to talk about pioneers in that sense because the work he's going to talk about relates, at least based on the title and the abstract, to this line of work, and in particular, a new data set that he had been working on for the last few years. So without further ado, here's John Hansen today. Thank you.
Thank you very much. So, thank you. So can I see first a show of hands of everyone that was born before 1969? Okay. Anyone born after 1969, part of today's talk will be a little bit of a history lesson, okay, if you haven't seen this stuff. Okay, so I'm going to give an overview of some of the work that we've been doing as well as how it connects to real-world naturalistic data. Some of the first work I did when I was a PhD student, I wanted to try and get speech technology into real-world settings. So as a graduate student, I collected audio on roller coaster rides. I didn't think I would have many volunteers, but I had too many students that wanted to go on the roller coaster rides. So I ended up kind of moving into other domains here. So today I'm going to talk, first, highlight a little bit about speaker variability. In naturalistic settings, we have lots of variabilities that introduce kind of challenges for speech technology. I'd like to highlight some of those. Next, I'm going to focus a lot on the diarization side of things. Those of you, obviously, who have not maybe worked on diarization, focuses on who said what, when, and how. Those are the factors there. And then I'll talk a bit about multi-channel diarization and content team type assessment. One of the things that we feel it's interesting, when you look at your cell phone, all of the work that you look at for your phone is typically one-to-one. And if you're looking at group dynamics, this is one of the areas we think that speech technology can be a big asset here. So then we'll look at examples of monitoring different types of communications. Prof-Life-Log will point a little bit to that. An educational training space called peer-led team learning, which looks at students kind of solving group problems together. And then speech and speakers from Earth to the Moon, which kind of implies the Apollo type stuff. So we'll highlight that. Okay, so I pointed out when we look at the concept of kind of speech communication, those of you who are born before 1969 probably remember, maybe not this telephone here, but when we think about telephone, we always think of point-to-point type communication. And still, when you look at your cell phone, you still work in that context. But today, we're more likely to see kind of naturalistic engagement here. One of the pioneers in language assessment for infants and children is Lena Foundation. And if you see the little recorder here, this has been available for the last 25 years. Close to about, I think, 8 petabytes of data have been collected from more than 65 different countries by Lena Foundation. I've been involved with that organization. It's a nonprofit type group. 2 of my students helped develop the language assessment software for infants, primarily looking at infants and children that might be at risk for some type of either neurological or communication type disorder. But one of the things that we can see is that more data is actually being made available, and clearly this offers some great opportunities to improve technology for assessing human engagement. The other aspect, though, is that when we go into these naturalistic spaces, we have much more speaker variability, and that offers many, many more challenges to ensure reliability of the algorithms. Another aspect here is the multi-speaker context. We're going to have many more people kind of working together. We'd like to understand, oops, I just lost my microphone. Hello, hello, yes. We'll have many more examples here of multi-speaker type context, voice-enabled type distance assessment as well. So kind of looking at the space here, you can kind of see all different types of kind of communication engagement in the car environments, maybe at home speaker, smart systems like this, or maybe meeting settings like this. And in these contexts, when we're looking at communication, we might think human to human, human to machine, but you also have prompted and spontaneous speech. These offer different modalities in terms of how we interact. If someone is speaking in a monologue, two-way conversation, or some type of group dynamics, this offers more challenges. So this kind of shows the variability of different types of things we might see for speech applications, and the variability obviously either across speakers or within an individual speaker offer bigger challenges in trying to achieve good speech technology performance. Now, I noted here, this is in the area of voice forensics. There's big challenges that exist in the voice forensics phase. We can look for speaker recognition, mismatch conditions, variety of different aspects in here. If you're interested in some of the forensics context, we have a tutorial that we put together in the IEEE Signal Processing magazine a couple of years back that tries to highlight a number of the different challenges that individuals have, both for speaker ID as well as for the forensic context. So if I look at kind of the variabilities here, one aspect that we see is vocal effort and whisper. This is a big domain that becomes a big challenge as the vocal effort and changes or is adjusted. An area that our group and myself have been involved in for probably more than 30 years has been in the lumbar effect space. So when you're speaking in a noisy environment, you're going to change the way you produce speech. And when you change that adjustment, you're going to change the characteristics of consonants and vowels differently. If any of you ever saw the movie Spinal Tap, you don't turn the volume up to 11. You actually dynamically adjust how the individual phonemes are produced. And that causes enormous challenges for speech recognition and speaker ID. Physical and cognitive task stress, these are factors obviously when people are moving around doing physical tasks while performing some speech engagement aspect. That physical or cognitive task will actually introduce variabilities in the speech production space. We had a couple of students who actually, interestingly enough, was interested in doing karaoke. And so we had people read and sing the same content. And what we saw was that if we look both at speaker ID and language ID, we did it for Farsi, Hindi, Mandarin Chinese, and English. We saw major differences in speaker ID and language ID if the person was reading versus singing the same content. So the actual text content is the same, you just lose the performance in ID and language ID and speaker ID. So this tells us that if you change the way you speak, you actually can kind of cause some big problems. So if you're talking on the phone, one little takeaway message. If you're talking on the phone and you think someone is running speaker ID, just sing what you actually are saying. Quite frankly, the ID performance will drop almost in half with that, okay? Other aspects would be like peak clipping here, and this seems like a trivial type thing. Someone said, well, just look for the peak. It turns out actually all audio that's released in the field has some peak clipping. Even if you go through the telephone network, if you look at TIMIT, we assessed probably about 40 or 50 different corpora that are available from LDC and ELRA, and we find that there's clipping in everything. So that part introduces some small distortions that are also a challenge. Session variability is a big factor. Language mismatch, clearly something that's been in the NIST SRE. Aging variability, Finian Kelly, who's one of the pioneers in this area, he worked with at Trinity College is where he did his PhD, but aging is actually another factor that people look at. And also in the area of non-speech vocalizations, when people are screaming, coughing, or whistling, there's also some level of speaker identity in that, but not the same as what you would see in speech. So I'm going to talk a little bit about Prof-Life-Log and PLTL, and then finally end up with a discussion on the Apollo corpus. So in diarization, we typically start off, we say we have some type of audio stream. In that audio stream, we can figure out obviously the text of what someone is saying. If you're not interested in kind of looking at all, doing full speech recognition, one could simply look at keywords. Maybe you're looking at different types of food if you're hungry in the morning. Another aspect is speaker ID and tracking, so just looking to see who is speaking and when they're talking. Topic ID is also a factor that's interesting. A lot of times this is based obviously either on the keywords or on the ASR output. And then the environment context. Can you figure out where the person is kind of talking based on some of the acoustics in the room? So these are all factors one would like to extract in an audio stream if you can for diarization. Aspects that we could look for here, well, when we look at this type of piece, usually for the general concept of speaker diarization, you're simply trying to identify which speaker is talking and just tagging those individuals. There's a variety of different toolkits that are available in the field. Almost all of them, pretty much I could say all of them, are really based on one-to-one type communication. You have a single audio stream, you're simply looking at someone talking. It could be, let's say, someone like myself kind of giving a talk as a lecture, or it could be two-way conversation on a telephone network. But all of these factors here tend to be kind of point-to-point type communication. None of these actually look when you have multiple people on multiple channels simultaneously looking at the audio at the same time. This is actually where you have much more challenges to kind of overcome. So these primary factors make it more difficult if you're looking at environmental context. Okay? So the one domain we kind of spent a lot of time on is this Prof-Life-Log. What this was is the Lena unit. It's basically a personal recorder. It can capture between 8 to 16 hours of audio in a day. Over maybe the last 10 years, I've recorded about 100 days of my life on this. It becomes kind of hard to release this because I was department head at my school for about 8 years. And you know, I have meetings, so I end up talking with students, unhappy campers, I'll call them if they're didn't do well on a test or something, or staff or other faculty. Anything involving that was really confidential, I would just turn the recorder off. But generally speaking, I had recordings all day long. These are all unscripted, naturalistic audio. You can kind of see either having meetings, walking in the hallway, or sitting at the desk. And so in these pieces, the things that we have to look for is, can we identify, you know, where someone is speaking and what they're talking about? So this shows kind of a profile of one of my days. So it shows here how much time there's speech versus maybe some background type discussions. If I look here, the environment, just based on the acoustics of where I'm walking and the sound that I have, maybe I'm in the office, in the car, in a restaurant. I'm not in a restaurant that long, but I think I had a meeting that day with one of our sponsors. Student Union is basically where the kind of the student center where people kind of go to get food or other things there, and maybe walking outside. And the other part is to kind of look and see how much someone talks. And so here you can kind of see primary speaker, although my students think I talk too much, there is a nice healthy balance here of all the people that are talking. So I'm not speaking all the time. So the idea on this is that you can kind of check to see who is kind of speaking. You can look to see the environment and maybe some of the background type characteristics. The nice thing about this is that I know we're very concerned about privacy and ensuring that we're not stepping on someone's toes. If you look at something like this, you're actually getting aspects about maybe the environment, how people are talking with each other, but not necessarily exactly what they're saying. So you're still preserving the privacy and factors along those lines. So a standard diarization system would require a speech activity detector. There's non-speech, you might use that for kind of normalization or enhancement, but speech activity detection, you get the speech, you do the diarization, look at primary versus secondary speaker. For the primary speaker, you might have some offline type text resources, a bag of words that you might use then to kind of get the keyword spotting system, and then a set of lexical terms that would allow you to figure out what the person is saying as a keyword spotting context. So I'm going to skip over some of these, but speech activity detection, one of the standard techniques one would look for. Primary versus secondary type speaker detection is one of the tagging aspects that one has to apply. So I'll mention here at least one of the speech activity detectors we put together a couple of years ago called Combo SAD. This was for the DARPA RATS program. And this is really actually the most effective unsupervised speech activity detector available, at least at the time. And the system, the way it works is you have an audio stream, you have 5 different individual features that you're tracking. Those 5 individual features are then fed into a principal components analysis and projected into a two-dimensional, a two-mixture GMM. So basically there's one-dimensional type feature here. And then you set dynamically, the system kind of determines this 2D PDF. It finds a decision threshold somewhere in between here and determines speech, speech, non-speech. And so the system here, because it uses these 5 different features, when someone is producing naturalistic speech, there's going to typically be some type of voiced information as well as consonants. And while other types of audio might trigger some of these factors, when speech is present, it's unlikely that all 5 of these features are also going to be turned on the same way as what you would see for speech. So looking at just performance here, this looks at the DARPA RATS corpus, and this is the speech and noise corpus by the Naval Research Lab. And you can see these are the 2 standard methods here, the G729 and G720. Those are the 2 publicly available methods. There's a single observation likelihood ratio test. SON is kind of a standard one you can see here on the green. Multiple observation likelihood ratio test is sitting here. And this approach, the HRM frequency multiple observation likelihood ratio test, is by Lee, one of Bara Wan's PhD students from UCLA. And that one sits along here, you can see. I guess it's this one there. And combo SAD, you can see, sits up on these. So the performance on combo SAD is extremely good. And quite frankly, it beat out, I would say, quite a few of the supervised methods that the DARPA RATS program actually had in the field. So this is one of the top performers out there. So that was for speech activity detection. The next thing you might want to be able to do is to look at speaker traits or speaker tracking. Is speaker A talking or speaker B talking? So in some of the Prof-Life-Log audio that we have here, we're kind of detecting to see how much time does the primary speaker talk. So see, these are all examples where the primary speaker is talking and the secondary speaker is not talking. These are cases where the secondary speaker is talking mostly and the primary speaker isn't. These are more balanced type interactions, and these really are just noise dominant. So if you're looking at audio from a daily setting, if you're sitting in this space, you're probably looking at some type of conversational interaction. Down here is probably the main person kind of speaking in a general setting, and back here, usually the person is listening to someone in some context. So that allows us to look at the different types and styles of speaking that go on. The speech recognition system, obviously we're using CALDI as one of our systems here. We look at finite state transducers and phone confusion networks. Those are the 2 methods that we had focused on. We've also looked a lot at word count type estimation. So this is an important thing if you're just trying to count or assess the amount of interaction that people have in speech. So the word count system looks like this. Run a speech activity detector, simple speech enhancement, special subtraction, a syllable count system, and LMS log likelihood MMSE strategy to look at the word count. So this is the equation here for the word count system, and we were running this in Prof-Life-Log. So with this, we can kind of look to see how much improvement we might get in word count estimation with and without some type of speech enhancement or with a better speech activity detector. So this kind of shows the baseline word count estimation is kind of, this is word count error. So anything kind of in the blue kind of shows the word count estimation. If you run an improved SAD, you can see that the performance actually usually increases at some level. Did better there. And this is word count running also with a very simple speech enhancement method. And you can see that improves in these, didn't help here, and improved on the rest. So these are in different spaces. A conference, this is actually one of the interspeech conferences. This is actually in a cafeteria, in the office environment, in the car environment, and I think this is at the conference banquet. So you kind of see the word count estimation there was not so good. So roughly, if you can kind of improve the speech activity detection, maybe run some type of enhancement as a front end as well, you end up improving word count type estimation. That's an important thing if you're looking at assessing diarization. So here just shows doing an assessment of word counts. This is actually at Interspeech 2012. This shows kind of the word count error. And when you hit the conference banquet where things are really noisy, the error rate goes up to about 19%. But you can see it drops below 5% here, maybe in the general conference, just walking around talking with people. If I'm looking here on campus here, conference room, cafeteria, auditorium, conference room, there's a lot more error, partly because there's more speech and echo and other people talking. Auditorium or other spaces here, you can see the error rates are typically below 5%. So system works quite well if you're looking at trying to assess word count context there. So kind of moving forward then, we still also need to kind of build a good speech recognition system. So one of the things that we focus on is looking at keyword spotting. So in keyword spotting, how do we find good words? Well, one of the things that we look for is we wanted to understand the differences between technical speech and non-technical speech. So we went back, we pulled, I think, 3 different interspeech conferences. We pulled all of the papers from those 3 interspeech conferences, 2,200 papers, 4.2 billion words just from those. And from the part of speech tagging, we could identify words that were more technical and words that were less technical. So this way we could kind of separate out in the bag of words here which words were going to be more frequently used as non-technical words and which ones would be more technical. So words like stop words, I, of, the, it, and, or, those are words obviously we don't want to actually focus on if we're trying to figure out what the person is talking about as a topic. Okay, I mentioned here in our keyword spotting system we do use phone confusion networks. That's one of the systems we had worked with, and turns out it actually works quite well. In the assessment here, this kind of shows in the environments how much time from the environmental sniffing, how much I spend in the office on one day. You can see that here I spent a lot of time in the office, here maybe not as much. I'm not sure what I was doing here. I was in the classroom here, so I was teaching a lot more. This was a conference room and something else. So this actually just looks at the noise in the environment. This is looking at the signal-to-noise ratio in the office versus the cafeteria, and you can kind of see that the office environment signal-to-noise ratio is much better, and in the cafeteria, the noise levels are much higher, so the signal-to-noise ratio is much lower. And then looking at the percentage of time from the primary speaker versus speech in general, you can see here that there are different areas, like in the classroom. I don't talk all the time. I ask students or people to kind of give feedback. We're asking questions in there. So you can see there's some type of a balance here between the primary and the secondary speaker, again, using that Prof-Life-Log. One of the bad things about the Prof-Life-Log is that it records everything, okay? So I had, I think, 4 transcribers transcribing a lot of this audio data when you're walking around. Unfortunately, they could figure out the number of times I went to the bathroom in each day, because when you flush the toilet, that comes up. So, there's some personal type things there that, are maybe not the best, to pick up. But fortunately, none of my students were working on this. I had 4 transcribers that were from the Speech and Hearing Sciences program that did the transcription effort on that. So this just kind of benchmarks here, some aspects here on keyword spotting. I just kind of put up a couple of different corpora and the keyword spotting systems we looked at. So if you look at TIMIT, obviously that's clean data. And so if you look at the miss rate at a particular false alarm rate, you can see TIMIT does really, really well. If you look at switchboard, that's obviously two-way conversation. It is spontaneous, and you can see you're going to lose some performance in going from TIMIT to switchboard. Prof-Life-Log, again, primarily one speaker. You're picking up other speech in there as well, but you're going to lose a little performance there. No-Tell is a noisy telephone channel corpus. It was actually recorded in the field. You can see you're losing more performance there. And the DARPA RATS, Robust Automatic Transcription of Speech, that audio had Dari, Urdu, Pashto, Farsi, and Arabic, those 5 languages. And so the keyword spotting systems we built were in Arabic and Farsi. And you can see, obviously, that performance also drops, is not so good. So at least it tells you a little bit about as you have prompted read speech versus spontaneous natural data, you can see that the recognition performance is going to start to drop, and we have to overcome those. This slide here kind of just shows a highlight of the in Prof-Life-Log word counts on different days. And so I think we had 8 or 9 different days in here. And on some days you can see I have maybe 5,000 or 15,000 words. On really vocal days, I hit 52,000, 53,000, and 57,000 words produced in a day. Okay? So you might ask yourself, how many words does a human actually produce in a day? Okay, well, at least in the Lena Foundation, if you look at infants and you want to actually have a rich environment for infants to hear when they're learning a language, a rich environment would typically be about 18 to 25,000 words in a day. Okay? So unless you're reading to an infant, you're really not going to be able to get that word count up. So this is an interesting or useful thing, at least to tell us on different days how many words you're producing, because we could also figure out the environmental context. We can figure out exactly where those words are being produced. And so my dean always comes to me sometimes and says, well, how much are you engaging with the faculty and with your students? So I can at least see here in research meetings, I produced 62,000 words over these days. Here with student meetings, 63,000, and in faculty meetings, 78,000. So I can say either I'm talking a lot or they're talking to me, I don't know. But at least there's a lot of speech being produced between in faculty meetings and also in student meetings. So that at least says there's a lot of activity. The other aspect one could look at is if you've got profiles like this on a daily basis, you can then start to analyze which days are similar to others. Okay, how close and how different are they? If someone's having a bad day or someone is maybe the engagement is not the same, so you can see in a day like this, there's really very little conversation kind of going on. There wasn't much on that day. You can see on this one here, there was a lot that went on in research meetings and so forth. So you can kind of look and correlate which days are similar to each other. So then I've talked about Prof-Life-Log. I'm going to move on now to another domain which also looks at using the same linear units, but this is called peer-led team learning. And this space is actually in a lot of the university settings in the US when people are looking at STEM, education, science, technology, engineering, and math. They've learned that if you place students in a group setting and you have them work together and solve problems collectively, they end up helping and reinforcing the learning experience. And so what peer-led team learning is set up is that you have one lead and typically 6 to 8 students. The way it's set up is that the students are all signed up for a particular class. The lead person gets a sheet of paper and says, okay, I've got the homework assignments or a set of problems from the teacher. All right, you two are going to work that first problem, you two are going to work the next 2 problems, and the 3 of you are going to work the next 2 problems. And what they do is they go to marker or glass marker boards along the walls, and they work in pairs for like maybe 30 minutes. And they all sit down, and then they take turns getting up and explaining to everyone else how they solve the problem. If there's any flaw in that, they get corrected or updated as a group. And so because of that explaining, you end up reinforcing the learning concepts. And that's where peer-led team learning is actually evolved. So we did a collection over a semester with chemistry. And students here sitting, you can see someone is sitting solving some chemical makeup here. There were basically 11 weeks we went through. There was 5 different groups in those, so we had 55 group meetings. The nice thing about this is that we had recordings each week. For each team, there's roughly about an 80-minute, 70 to 80-minute session that goes on there. In addition to that, after the session was done, we had each student fill out a questionnaire to basically give us feedback on how they felt the learning experience was for this. So if they're feeling like they're having challenges or it was helpful to them, we got that feedback. So we did this for chemistry. We also did this for calculus. And we went through, did all the collection. Unbeknownst to me, it turned out my daughter, who was a biochem major in our school or in our university, ended up sitting in on this. She was on the calculus one. I didn't know this. And so one of the students were kind of working something, and they played one of the examples, and I said, that's my daughter. And I didn't realize that. So, the prospects here, this works well. They're all wearing these little linear units. We have them set up in little pouches. They're in little zipper cases. So this way, it's not like someone sticking, this microphone right in your face and saying, how are you going to solve this calculus problem? So because they're wearing those units, we're able to kind of work and analyze those aspects there. In some of the designs here, we ran a pipeline here for PLTL, speech activity detector, diarization. And then after the diarization, these are the types of things we look at in the peer-led team learning. Who's dominant? And we look at leader-follower concepts. Was the group cohesive? Was there anyone being argumentative or someone being unhappy about something? Was someone more curious or someone kind of contemplating or saying, well, what would happen if this were true? So we can look at who's asking questions, who is more driven to try and take the next step beyond what the actual question was. And what are the most important segments or hotspots? Can we find those factors in there? So the thing is, if you look at a student over the whole semester, you can say, did they start off poorly and do better? A lot of times students walk in and say, look, I'm an A- student. I want to get an A. But if I'm working with a C student who wants to get a B-, am I going to catch, this as an illness or something, right? And the answer is no, because by explaining it back to any student, you reinforce your own learning concepts. So people learn independently, and they support each other. So this aspect there allows us to look at the analysis side. From our pipeline here, you can see we have multiple recorders that are all being recorded at the same time. We run speech activity detector, feature extraction, normalization, and splicing. And we go through and do the segment characterization here. We use a stacked autoencoder with bottleneck features here for the splicing and feature fusion. Unfortunately, I can't go into a lot of the details because what I'm trying to cover here, but at least one of the things I can show you is maybe the assessment on who is talking in the pure team learning space. So this shows kind of the automatic system. We see that the leader is talking, but that's only because in that block, this is actually the leader's recorder. So the leader's recorder obviously would capture more of the leading person in there. That person is not supposed to be teaching. They're just supposed to be facilitating. So at least here in the automatic system, that shows the leader is talking, and then the leader actually floats around and at least gets information or interacts with all the other students. There's at least 6 of those students in here. This is ground truth labeled human results, and you can see there's a little bit of an offset there in terms of the amount of time the automatic system said the leader was talking versus the human tagging. But at least it shows there's good correlation there in making that type of assessment. Okay? We've also done some more advancements here. We've used the SyncNet embedding systems here with multiple convolutional neural network layers and fully connected layers as well. And we pulled off different features here to see if we can improve the diarization performance on these peer-led team learning. Again, I'm going to run out of time here, so I'm just going to give the highlights here. We're looking here primarily at vanilla transfer learning aspects for the algorithm, not for the humans, and looked at some ways to try and improve diarization performance with the SyncNet embedding system. So this shows at least without a principal components analysis I-vector system, the F2 average sits right at this spot here. It's between after the convolutional neural net and before the fully connected layers. You can see that the error rates here are actually dropping nicely here. And if you're using F2 max, you can see that performance the performance improves dramatically when you incorporate PCA and you move from I-vector system back to an F2. That's the second feature set there. So with SyncNet embeddings, you can improve the performance for the diarization side. Okay, so now I've given you kind of like the sampling across the area for Prof-Life-Log and PLTL. Now we're going to dive into Apollo. Okay, so this was an NSF-funded project. A lot of times NASA tries to take credit for this. They've done some great job. NASA is fantastic. But NASA does not have a budget for archiving. Their concept is, what are we doing today and moving forward? Anything that happened behind in time, they'd like to hold on to that. If someone needs access to that stuff, they're more than happy to let you get access to it. But they're not putting money and resources into archiving what they did. They're always focused on where they're going. So that was the main reason that we went to NSF here to get the support. And I have to say, without NSF, this absolutely would not have been possible. But we took a 3-year funded project and we stretched it to almost 6.5 years. So that was due to a lot of creative budgeting on my side, just trying to make sure I can keep students supported. Now, I kind of point out, you know, if you look in life, there's certain exclusive clubs that one can belong to. Probably the most exclusive club on the planet are the moonwalkers. There's only 12 moonwalkers, not the guy that went like this right here. That's not a different moonwalker, okay? Only 12 moonwalkers exist, okay? And of those 12, unfortunately, over the last 24 months, 3 have passed away. Bean, Young, and Eugene Surin from Apollo 12, 16, and 17. Now, in the span of the 5.5 years I was doing this, I met Eugene Surin. If you can believe it, I was walking in with some tapes to try and digitize stuff, and there was a guy sitting in this sound booth recording, you know, some audio, and I'm walking with my NASA facilitator, and he stops and he's looking in there. And Eugene Surin, a moonwalker, he's sitting there recording audio that's going to be played on the tour buses that NASA drives people around. So if you think, this guy has a lot of stuff that, you know, thinks he can spend his time on, recording audio that you're going to hear in the bus from a moonwalker is something that I didn't think a guy would volunteer his time, but he would do that. So Eugene was the 12th and last man to walk on the moon, so he made sure he was the last person to leave that footstep there. If you ever see, there's a movie called From the Dark Side of the Moon, and it's actually a very interesting movie. It starts to contemplate maybe a little bit about when you look at walking on the moon versus on Earth. And I think it was Alan Bean in that movie. He was saying he walked on the moon, and then he came back to Earth, and he was standing in line at a grocery store. And a woman in front was kind of complaining about how much the price of bananas had gone up. And Alan was saying, last week I could take my thumb and put it over the entire planet, 6 billion people. And this woman is complaining about banana prices. So he says your perspective on life kind of changes when you walk on the moon and you kind of come back. So one of the things we wanted to try and do with this is all the audio that was collected by NASA is all analog. Analog. I know most of you don't know what analog is. It's on tape, it's old stuff, okay? And the problem with that, it doesn't last forever, okay? So we wanted to kind of pull these things out. There's still 4 moonwalkers alive: Buzz Aldrin, David Scott, Charlie Duke, and I met Charlie Duke as well. He came to our campus maybe last fall along with 2 other Apollo astronauts. So these are the folks that are there. I got to play some audio for you. So this is some audio that's coming from Apollo 11.
Apollo 11, this is Houston through Canary, over. Roger, and I'd like to pass up your Delta azimuth correction at this time under a copy. Okay, Delta azimuth correction is plus 0.22. That is plus 0.22, and we do recommend the P52 alignment, over. Okay, we'll go ahead with P52 and the designational plus 0.22. Roger.
All right, so now you know what the P52 alignment is, right? No, it's okay. So one of the things that you hear is you hear these little blips that are coming in. Those blips are called Quindar tones. And the reason for this is because when NASA, what they realized was that when the astronauts talk, everyone else has to be quiet. So when the astronaut talks, a Quindar tone starts. And the tone from when the astronaut starts speaking and when they finish is at slightly different frequencies. But this was something that was actually done in the communication system. Now, the audio loop that you're listening to is called Capcom, or the capsule communicator. There's one person in mission control that's allowed to talk to the astronauts. You don't want 500 people trying to tell the astronauts what to do. So there's only one person that gets to talk to the astronauts. In the beginning there, you may have heard, this is Houston through Canary, okay? Well, when you're talking to the moon, you don't have a line of sight directly to the moon. So there's 6 or 7 listening stations across the planet where NASA had to route the audio through, or the communications through, in order to talk to the moon. So they're talking through the Canary Islands, okay? The other, one of the other listening stations was Australia. And there was a spot there where the Apollo astronauts were trying to talk to Houston. They weren't responding. It's the only time that Australia actually responded. And then I think the astronauts and the Australians said, when you get back, we should have a beer together. And some Australian beer company, not Foster's, picked up on that and decided, let's ship them a case of beer. And so there's a picture of the astronauts with these controllers sitting on this case of beer. So the point, McCandless, he's one of the Capcoms, or the capsule communicators. He's the one talking with the astronauts there. If you didn't catch this, it was Neil Armstrong first talking. Michael Collins is actually commander for the lunar orbiter. And so that's why he was the one that popped in there, because this is a directional type piece of information that needs to kind of be given to the person who's piloting the orbiter. So in the NASA type thing that we were looking for here, we went into this effort with the notion that we wanted to understand how people work together to solve problems, okay? So in this JSOL meeting, you're a whole team of people working on different problems. Some work individually, some will come together as groups. So you might say, if I work together as a group, how do I solve my problems? So that's what we wanted to look for here. We said, well, let's set up a timeline, and then let's look at maybe astronaut. The astronaut, they have their own cameras. There's also transcripts available. There's also conversations and interviews and other things that go on. And there's maybe some GPS or some other information that we might have. So the thing is, you have the audio that goes along. We said, well, what we wanted to do was to actually first generate transcript and metadata for the timeline. And then if you say, well, I have a picture. The picture looks like it's the spaceship taking off, the Saturn V rocket taking off. Well, you want that at the beginning. You don't want that at the end. So one of our collaborators on this project, Doug Ord from the University of Maryland, he's a archivist, but also a closet Apollo aficionado. He can actually tell you what the astronauts ate for breakfast before they went onto the rocket. Really knowledgeable about a lot of stuff. And so Doug wanted our text transcript so he could then go and kind of start linking images and other factors in there. So that was one of the things we looked at. So when we look at this, you have the astronauts that are in outer space. They're kind of talking to capsule communicator who is in MOCR, or Missions Operation Control Room. So this is kind of the space where everything happens. In addition, when you look at all the people that are sitting in these different spots, they don't do it all themselves. Behind every spot in this area, flight director sits here, there's a back room. And this back room, these are the support staff that are actually helping each of the individuals there. And so all of the audio that's captured in here is recorded on this reel-to-reel system. There's actually 4 reel-to-reel systems. This is called SoundScriber. That's the name of the unit. It was built in the 1960s. It's the only system out there that records 30 channels. Okay, it's actually model number 2. Okay, model number 1 is in pieces underneath here in the cabinet, so there is no other system there. So all of that audio is collected there. There's actually historical recorder 1, historical recorder 2. There's an upper and a lower deck. So the idea is that if you're recording one and you're running out of tape, you can't tell everyone, stop, we got to swap the tape. Okay, so they have another tape that they start running before this one finishes, and that allows you to capture all the audio. So the audio is recorded. Each one of these tapes is roughly about 14 hours of recording. I would have brought one with me, but it usually takes me about 2 hours to get through TSA in the United States when I walk through with one of these tapes, because I can't bring it through X-ray. Okay, so NASA is not too keen if you X-ray those tapes because they're analog and they get damaged. Anyway, so this is the Mission Operation Control Room. This fellow is a guy named Greg Weissman. He's one of the best guys I know from NASA, and he's working here on SoundScriber. Now, any of you in the front row here, you might see this little yellow cord here. You know where that yellow cord is? How many of you have a car with a roof rack? All right, there's a thing you put on top, it's called a bungee cord, okay? Kind of holds the luggage on the roof. That's what he's got there. Why does he have a bungee cord? Because he's trying to maintain the tension on the tape, okay? This thing was built in 1962, okay? So it doesn't work too well, right? And so when we wrote this proposal to NSF, we said, well, we assumed that they had digitized all this stuff. We drove down to NASA and said, okay, you're going to just give us all this audio on a hard disk, right? And they said, no. We're going to point you in the direction of this closet where we have all the tapes. And here's SoundScriber. Take whatever you want, okay? We thought this is not going to be easy because we started looking at this, and this is one of the original read heads. It only plays or only picks up one track. There are 30 tracks on each tape. Each tape is 14 hours long. It would take you 1 month to digitize one tape. Okay? So that means it would take 172 years to digitize all of Apollo continuously. Not a solution, okay? So we said, well, we need to go and come up with a better solution. So given the name of this manufacturer of this head, which went out of business a long time ago, we found a manufacturer in New Jersey that could actually produce heads. He was a magnetics type guy. And so we sent him the specs for this. We went and got the original specs for the head. We had a 3-track head built. It cost me about $5,000 to build this head. We went back down to Houston, and we said, NASA, we've got this head. And they said, great, do whatever you want to do, okay? So they let me, some geeky professor, walk in and actually put this tape, or this head, in this recording spot. So you can't see this, but if you look right in this spot here, that's actually the adjustment for the head. What it is, it's a little wheel that you rotate. As you manually rotate that wheel, the head moves this way in and out, positioning manually where that pickup is going to be. So with the 3-track head here, we could get 3 tracks at a time. We spent about 2 weeks, did some recording on this, found it would work. Then we went back to the manufacturer and said, 3 heads are great. We want a 30-track head. This is a 30-track head. Cost me about $12,000, okay? This is not something NASA paid for. And NSF, I had to go back and get extra money from them. They were really generous and supportive of this. We got the 30-track head. We went back down to NASA. They said, there it is. Do whatever you need to do, okay? Now, if I went down with my student, if we messed this up, this is the only playback system. I had to actually go and rewire this because this is a 30-track head. There's like wires that are hanging down. You can't have these 30 wires hanging all over the place because you've got tapes and everything moving around. So we had to go in underneath and rewire the whole thing. My student looked at me and said, I can't do this. And I said, I was a technician. I kind of put myself through my undergraduate days. Don't worry, I'll do this. Just hand me the parts. So I was on my back underneath rewiring this myself. Just think of this. You mess this up, there is no other playback system. So I told my student, if we screw this up, we're hopping in the car and we're driving to Tijuana because we're not coming back. Someone is going to get really mad at us, and I don't want you to be the fall person for this. So we went, I had that in there. We had to do some adjustments because when the manufacturer, when we had them produce this, they unfortunately didn't put the grounding wire on this correctly, and so we had some crosstalk in there. We had to ensure that there was no crosstalk between the channels. You're going to digitize this? Yeah, I don't want to do it twice, okay? So we got this adjusted. I let my students sit there, if you will, for 4 months. 4 months. Every day he came in and he just digitized tapes. This guy has the most patience of anyone I ever met. So there's the SoundScriber system. It's in a small little room. That's Abhijit. He's one of our staff members. Lakshmish was also, actually Lakshmish, he's Canadian. He was here, he grew up in Toronto and worked for Nuance. Had him down there. Alan Stouffer is another student that was down. He was the one helping with the 3-track head. And this is Tuan. He was the one that's the 30-track system we put together. And he sat there for 3.5 months digitizing tapes. So he has enormous patience. On each of these tracks, now literally there's close to maybe 600 or 700 of these tapes. We digitized 72 of them. That produced about 19,000 hours. Each of the tapes has kind of a track sheet that looks like this. Each of these tell us exactly which microphone recording location it was on. And if you look over here, we're saying, well, here's all the tapes. Where did they land on the moon? We found the tape with someone took some like yellow tape there and wrote moon landing here. This is actually the documentation of the moon landing here. So that's where we got that. So we spent time, now you have the physical aspect of digitizing it. Once you digitize it, then you got to organize it and make it useful. So we pull this out. If you look, at least for Apollo 11, went 8 days, 3 hours, 18 minutes, kind of looped around like this. And so we captured, obviously, all the audio that's going through there. That's one of the things we're getting. The other part we looked at is we started analyzing like the astronauts. We said, well, how did the astronauts change their voice? Well, realize, when you're in space, you're going to sound different, okay? So these are actually just fundamental frequency distributions for Armstrong, Buzz Aldrin, and Michael Collins. Collins, unfortunately, didn't get to walk on the moon, but Buzz and Neil did. And so we got, their pitch distributions for when they're sitting on, I guess, Earth, getting ready to blast off, and then going to the moon, and then walking on the moon, and then coming back. So you get to see how their voice characteristics change. We also looked at their speech model characteristics. So we just trained a GMM, and then we looked at all the Gaussians and tried to see how do they differ depending on different phases when they're on the moon, traveling, launch, and on Earth. So you can kind of see how their acoustic, phonetic spaces evolve and change. Okay, so this was actually something particularly interesting in understanding how voice variability is introduced in there. I mentioned also, again, about the MOCR, or the Mission Operations Control Room. These are all the seats that are sitting in the Operations Control Room. I will point out Tuan, the student I had who was there for 3.5 months. The director of communications for NASA kept walking by this one room and seeing this poor kid in there digitizing these things. And he asked him, what are you doing? And he said, well, I'm trying to preserve Apollo, and I'm doing all this for a project. He said, when are you leaving? Next Thursday. He said, show up on Tuesday, wear a nice shirt. And so what the director of communications did from NASA, he assigned a photographer to this kid, and they gave him a private tour of all of NASA. But the cool thing that this kid got to do is he got to sit in the flight director's seat. that Gene Kranz sat in for Apollo 11 and Apollo 13. He sent that to his parents, and they started crying. It was cool. So when you look at these things, one of the things that you have is that all of these audios are actually recorded on multiple loops, and so it becomes a big challenge here. So if you look, everything is not just one-to-one. A loop is like a party line, so you can have anywhere from 3 to maybe 30 to 35 people on that line. No one is talking at the same time because they're very respectful of each other, but if 2 people are talking, let's say if I look at FIDO, that's Flight Operations FIDO should be the Flight Dynamics Officer. So that person is looking and making sure that the rocket is going in the right space. While they're talking, you'll hear the CAPCOM, or air-to-ground communications, on top. So you have layers of stuff that's going on top of the things there. So we'll move through this. This is the flight director there. I think we have some audio coming in here. So in these loops, CAPCOM talks to the astronauts.
1202 alarm. Yeah, same thing we had. Flight Metro. Now, 6 plus 25. 6 plus 25. We're going that flight. We're going that alarm. If it doesn't reoccur, will we go? Right. He's taking it up in each now. Raj.
All right. He says Raj all the time. So they're talking about the 1202 alarm. This is one of the alarms that went off. It was one of the things for Apollo 11 that was a challenge for them. Sounds too loud. Yeah, they had to pull the audio down. I'll go back. But so at least go through, what you'll see is that there's lots of audio kind of coming through. There's different people that are talking. One of the things when you're looking at this, CAPCOM talks to the astronauts. CAPCOM also talks to the flight director. So the flight director is the person who kind of coordinates everything. All the controllers are in here, and all the backroom support staff are kind of supporting those folks there. So the diarization side, we have each of the individual channels. There's 30 of them. Of the 30, channel number 1 is iRig. That's time code. It just tells you the time value that you have in there. That's an important thing because it synchronizes all the channels. There's one channel, it's called Public Affairs Officer. That's actually the thing that's transmitted out to the various news, TV, and radio stations. And then the others are all kind of groups. So we run speech activity detection, feature extraction. We're looking at overlap detection. That's one of the factors we have to figure out. Primary, secondary speakers. We do speaker ID and tagging, and from that we do a full speech recognition. So we're running all of the audio through a speech recognizer in order to be able to process this. And once we get this, then we can kind of pull off other metrics that might actually be of interest there. Because of time here, I'm going to skip past these two. We did some other work here for speech activity detector with CNNs, but because of time, we're going to skip past that. And we have also looked, so I mentioned here you could look at other factors in it once you get the audio pulled out. So one of the things, I had one student who was working on sentiment assessment. So this is actually the sentiment of the 3 astronauts for the entire 174-hour mission for Apollo 11. So you can see, there's spots where the sentiment is positive. They're looking at Earth from space, viewing maybe the moon from space. A couple of spots here where there's some technical problems, a difficult maneuver going in here. There's a spot there where Neil Armstrong is actually trying to land the lunar lander. And unfortunately, so he did one thing he shouldn't have done. When the lunar orbiter and the lunar lander separate, there's actually 2 computers on the lunar lander. One that's for docking and another one that's for landing. Neil forgot to turn off the power on the one that's for docking. So while they're flying to the moon, or trying to land, the electrical consumption of the power is going at twice the rate it should be. And that really doesn't sit well. So they had to figure out why that was happening, and that's one of the alarms that was popping off there. But at least here you can see the sentiment that comes up. I mentioned also that we had to do speech recognition. So we have DNN-based systems that we use to kind of build our recognizer. Unfortunately, you have to actually find a language model and a lexicon that's going to work. NASA actually speaks in really technical type stuff. And so in order to do that, we went and pulled books, all kinds of articles to try and build a language model. In the setup here, The language model has to be specific for a particular mission. They landed in the Sea of Tranquility. That's one of the regions in there. So for the Kali-based system we worked with, we had features here, DNNs. The ASR vocabulary size is about 40,000 words. In order to get that, we actually pulled 4.2 billion words in order to build the language model. And so all 19,000 hours are publicly released. The language model is released, and the lexicon is also released. Okay, so that's all been given out. We took we have 2 clusters, a GPU and a CPU cluster that we processed audio for about 8 months. And we had another CPU cluster that was on campus, so it was like shoveling coal into a furnace. We kept those 3 clusters running for 8 months to process all 19,000 hours. We went back to NASA to export control to allow them to release all of this. They said yes, it was good. And so here we just show some of the multi-channel audio. So one of the things that we look at is if you're running speech recognition on one channel, you may have more noise on another. So if you can identify similar audio blocks, you can use one channel to help improve the recognition on another channel. So we did that for one of our setups here. And this kind of shows the improvement in diarization. So if you're looking at the multi-channel system here versus the base model, running Liam or the base model, you can see the diarization error rates here are really bad. For our diarization toolkit, the performance is quite good. In the multi-channel mode, you can see performance improves a lot. And if you look at multi-channel plus overlap detection, you can see that you get even a little extra boost with that. So the multi-channel scheme actually allows us to leverage and produce more benefits from this. Part here I'll point to is that we can also generate something here called a chord diagram, so that identifies various people that are talking, Neil Armstrong, Michael Collins, and Buzz Aldrin. These kind of show maybe for about a 4-hour window how much time the capsule communicator is speaking, how much each of the individuals that are in the group are talking. We can also look to see who they're talking with. So that shows the connections on the interactions there. See, sometimes it looks like someone is speaking, but they're not talking to someone. They're just actually saying things just for general information. So from this, we can look at conversational turn analysis, word counts. We can also look at sentiment, emotion, and stress levels, and kind of automatically tag that information. When we released this, one of the things that we saw, we had a lot of people coming to us saying, hey, my uncle or my grandfather or my best friend kind of worked in NASA. You know, can you kind of bring them to light? And so one of the things we started was this concept of bringing the heroes behind the heroes to the forefront. So I have one student that is working on something called Finding Waldo. Okay, so if you know who Waldo is, it's kind of that guy there. And so what we do is we find somebody in mission control, and we have them give us their picture, what they look like in 1969 and what they look like today, and then we go through and find all the audio from that person and go stick it on our website. So now if you had somebody working there, you could go and listen to everything they said while they were actually in the space. We did this for at least a number of people. We're looking at the audio and here, pulling these pieces out. These kind of show the different content that we're pulling off. And here, these are some audio from Gene Kranz and Charlie Duke. So it's interesting, Charlie Duke was a capsule communicator for Apollo 11, but Charlie Duke also was a moonwalker. He, what NASA did is they had a lot of the astronauts be the capsule communicator because they knew firsthand what the training of the astronauts were. And at some point, he was going to go into space and someone else was going to be capsule communicator. So we have some audio examples here. I'll just play one of them for time reasons.
And 11, I have your visual pad and consumables update whenever you want.
So you can still hear the Quindar tones in there. You can hear some hum, realizing that this is 1969, so there's lots of cables and stuff running all over the place. There's lots of hum and a lot of other types of distortion that are in there. So I'm going to wind up here. Apollo 11 is a movie that was released, okay? I'm not sure if it was here in Canada, but at least on Sunday, it was broadcast. It was in the movies, at least in the States, in March and April timeframe. And so when CNN went to make this movie, one of this was the actual pitch that they made, the movie studio made to CNN. So it was called First Steps, and they kind of say where they're going to go through, and this was the storyboard that they put together. And the challenge that the movie studio had was they had a lot of silent video. NASA had a videographer that had a 70mm camera that went in and would take video of you, but it's only silent. So they had all of this video and no audio. So they started looking at the person and saying, can we read their lips? That's what they were trying to do. So I'll show you an example here. So this is the original video. And you can see his lips are moving. That's actually Charlie Duke. And there was someone at this movie studio that was sitting there trying to read the lips, okay? And he said, oh, we think he said this. And then they ran to NASA and they said, can you give us this audio? And they said, we can't do that, but go find this guy Hansen up at Dallas and maybe he can help you. So they contacted me and I said, well, it's okay, can I release the audio to them? They said, yes, do that. So I sent them our hard disks. We had diarized everything. We generated a transcript file, an Excel transcript file that has all the transcripts, links to all the audio. So all you had to do was kind of search for the text, find it, click this, you get the audio. The next day, they were sending me back video where they stitched the audio to the silent video. Now think about this. Someone recorded this over here. This is actually recorded from the headset, okay? And so if you look here, this is so that's the audio there. Let's say we're running out of time, so we'll skip past it. And now this is the stuff stitched together. So you could see in there, he said, check the breakers. It's synchronized perfectly. You see also spots there where there's no video. It's not that something was wrong here. They only have the video for the spot. The audio is continuous because it's coming off his headset. So they literally glued the audio from the headset to the silent video over here, and that's what you're going to see. So in this movie, okay, speech technology diarization actually made the movie possible because all the video that was taken in Mission Operation Control Room was silent. You don't want to go to the movie and see silent film. It's not so helpful, right? So by stitching these together, they were able to get all the audio. So our group is actually cited in the movie credits. Okay, we were kind of happy because the students, we were working on all this and they finally actually got something that was kind of neat in there. So I'll play another example in here, I think kind of just interesting here. I'm playing this one here. Okay, so he's kind of happy they're moving along fine there. So I'll just mention, over the last year and a half, we've had probably like 24 interviews for radio and TV. So NPR in the US, The Hill was a publication from Washington, D.C. ABC News, there's another archive here. KERA is the public radio station in Dallas. There's another one in Houston that interviewed us. Also the Discovery Channel did something. NSF put us on the front page of the NSF website. NBC picked us up and did a release on this. About 2 weeks back, NTK is the national TV station in Japan. They sent a group of 4 TV people to kind of do an interview down in Houston with us in the space there. So we got a couple more from ASE and a few other places. So I'll say the audio is all available, okay? It's 19,000 hours of audio that's available. We initialized a challenge for this Interspeech 2019. 155 organizations from 35 different countries have downloaded the challenge corpus. That's roughly only about 100 hours to start with. And there was 110 systems that were submitted. 15 teams were received and evaluated in the setup here. And so this represents a bunch of the different students that were involved in putting together the website and the support for this. This is the Explore Apollo website that actually you can go and listen to some of the audio in there. I'll mention here on the next steps, I know you've listened to me here for the maybe past hour. I've got a questionnaire here, and the reason is because we're going back to NSF, and NASA wants us and would like us to actually go and digitize the rest of Apollo. So we've got 19,000 hours we've pulled off here. there's over 200,000 hours of audio that's still available, but it's all in analog, okay? So we want to actually give this away. Everything that you can use, you know, there may be someone here from Google. If there is, I apologize. But Google has all the audio they possibly want, okay? In a university setting, you don't typically have all the audio you want. Also, you don't typically have naturalistic audio. So this is a case where over maybe, you know, a 7-8 year window, you can get audio from many, many different people multiple times. So if you wouldn't mind maybe kind of taking one of these and just maybe filling out and trying to get it back to me today, I would greatly appreciate it. It allows us to kind of try to understand what the community wants and how we could kind of give something back to the community. So I'm going to stop there. I'll thank a lot of students, staff, and especially NSF for the support here. And I'll stop at that point. Thank you.
We got audio, very good. So first of all, thank you so much for doing this. I mean, it's such a great part of our history, so I'm very, very excited about it. My question is actually twofold. After doing this, 19,000 hours, what would you do different and what surprised you most?
What surprised me the most was that NASA, so I would think NASA is a government agency. If you, I don't know if you're from Canada, but if you're from the United States, the government agencies in the US are mind-numbingly difficult to deal with. I apologize if there's any US government agencies in the audience here, or listening, I realize that. But NASA just opened the doors, and every time I showed up, they were happy to let me come in and do things. I guess what surprised me the most is I just expected all this to be digitized. And the reason this took like 6 years to get done versus the 3 years we proposed was because all these obstacles that just kept coming up. And quite frankly, I had just students that said, look, we want to get this done. It's good technology, it allows us to do an algorithm, but it also allows us to maybe help preserve, you know, a piece of history. And, you know, we didn't set out to do this because we knew that 2019 would be the 50th anniversary. But a month from like today, July 20th, is the 50th anniversary of the moonwalk, right? So I would say probably one of the things that surprised me the most is the level of professionalism that everyone in NASA has when they work. You don't hear them like joking around. I mean, they'll make a joke once in a while. There's one spot, I think, where Buzz Aldrin is looking at the Earth and he sees nothing but ocean. So he asks NASA, could you turn the Earth, because we'd like to see a little bit more of like, you know, the United States or America or something, and NASA said, no, we can't do that. And there's also other spots. There's like a sensor. There's a flight surgeon that basically is monitoring heart rate and breathing. And technically, that's not supposed to be released. If you see this in the movies, it's going to be rebroadcast here in July. The flight surgeon actually tells what the heart rate is for the astronauts, and that's actually illegal. They're not allowed to do that, but they did for the movie. And so there's one spot where the sensor keeps like malfunctioning for Buzz Aldrin's breathing system. And they're fiddling with this, the flight surgeon and Buzz Aldrin and capsule communicator, as about 15 minutes. And at some point, Buzz says, well, if I stop breathing, you'll be the first to know. Okay? And so that's one thing. The other part I'll just mention that's odd, so I'm over 50. I was a little kid when they went to the moon. On the PAO, Public Affairs Officer channel, somehow the TV feed from ABC, CBS, and NBC News or stations got recorded onto this. And I heard commercials that were from 1969 that were in there. I heard one mission control person, you know, they land on the moon. There's roughly a 6-hour window before Neil and Buzz are gonna walk on the moon. And one of the mission control guys, they don't have a cell phone, right? And nothing. So he calls his wife and sets up a date to go to, you know, the local restaurant to grab something to eat. And that was recorded on the tape here. And I asked NASA, are you okay? And he goes, yeah, there's, you know, they didn't say anything bad. they're human. They're actually doing these things, and that's what it was. So I think it gives a little bit of a snapshot of a human, people that are just average people that are trying to solve a problem. And I think that part, to me, kind of translates to how you learn in an educational space. So thanks for the question. I think he's the only gentleman with the chat.
Hi, John. That was a wonderful talk. So a quick question: there were communication in the in the NASA center between people. There were communication between Apollo and the NASA, and there's communication between astronauts. In terms of Diarization and ISR and everything, how are the performance with each category of communications? Because probably within the NASA they cross-talk a little bit more. I suspect, because I want to try to see it when they have communication with the astronaut that were more well-behaved and there was this tone saying. So do you have any analysis how the performance are doing in each scenario of communication?
So the thing is, for different phases of channels, there's more like natural, like just two people talking. And there's spots where there's much more of a group dynamics. So if you know, when the Saturn V rocket lifts off, it lifts off from Kennedy Space Center in Florida. So the rocket literally lifts off from Florida. Kennedy Space Center in Florida has control for 10 minutes after liftoff. After that, control goes to Houston. So there's Johnson Space Center to Kennedy Space Center, okay? And so here, everything is being recorded over here in Houston. So the audio goes back. So there's lots of these, like you'll hear feedback, you'll hear these other loop type things going in. I've got some silent video from the National Archives where someone took a video camera and just showed literally the miles and miles and miles of cabling that were needed to actually get to the soundscriber to record this. Because you have people sitting in different buildings, somehow it had to get to that spot. So I would say there's certain channels where the noise level is much higher and the distortion, tones and other stuff are in there, and there's others that are better. It's also the case when you're literally putting on a tape that's 45 to 50 years old, the tape stretches. So when we passed all of this to Neon Films, who made the Apollo 11 movie for CNN, they had to do some pitch duration correction as well. So there are other factors in there that they had to make the adjustment. But for Diarization, yeah, the error rates can be quite wide. You know, you'll see things that are really bad and things that are much, much better, and it depends who's talking. You know, some of the folks that you're listening to here, I'm sorry, it sounds like they literally went to some rural ranch or farm in Texas and pulled the person off because the Texas twang in there is like really, really strong. So.
You were mentioning that the tape was not constant, the speed of the tape. Right. So it has consequence on the frequency, the pitch frequency. Yes. Have you noticed that? And did you try to correct that thing?
Yeah, so as the thing rotates, right, it maintains tension on the reed head. So there's a rubber wheel that maintains the right speed for the tape. That rubber wheel had to be replaced. So it was one thing NASA did. They knew we were going to come in and do this. They actually found the guy that was responsible for maintenance on this unit. They had him come back in, and they upgraded the motors to turn that actually rotate the tape, and they put a new rubber pinch roller in there. That pinch roller, without that, because it's rubber, it becomes oxidized and like hard rubber, so it doesn't give the right tension. That's the reason Greg had kind of those bungee cords in there. We don't need the bungee cords now. It actually works perfectly fine. And it's just amazing that these tapes have just stayed and worked so long. They haven't deteriorated. I'm kind of shocked NASA, like when we made the request for them, NASA dropped these tapes in these little cardboard boxes and just shipped them through the US mail. If you can believe it, yeah. So if fortunately we don't get ice storms, if it was here in Montreal and it was in December or January, if this box dropped into a bucket of water, you would have lost them all. And so they just mailed all of those things to NASA in Houston, and we're opening these boxes and trying to figure out all the tapes. I had everything spread out on one floor. they keep them organized. I will say for Apollo 13, we did Apollo 13, but there were 4 tapes that were missing. So if you see the Tom Hanks movie on Apollo 13, he says, Houston, we have a problem. That was one of the things that was missing. And so, I kept going back to Greg and the folks at NASA, and surprisingly enough, last December, they did find those 4 tapes. So they said, well, we want you to come back down and digitize these 4 tapes, and by the way, could you digitize everything else? And that's why we're going back to NSF to see if we can kind of get a project to kind of do this for all of Apollo, and hopefully make this available to everyone in the field. So.
I think we're about out of time, but as you know, there's some scheduled time to meet with John this afternoon, so don't forget to sign up. And without further ado, thank you so much for that talk.
Thank you.
Thank you.